Have you ever looked up at the night sky, filled with countless twinkling stars, and wondered just how big it all is? It's a question that has fascinated humans for thousands of years. We see stars, planets, the Milky Way, and it feels like a giant, unchanging painting. But what if I told you that this painting is not only getting bigger, but is stretching apart at incredible speeds? It sounds like something from a science fiction movie, doesn't it? The universe isn't just a static collection of stuff. It's active, dynamic, and ever-growing. This single idea has completely changed how we understand our place in the cosmos. The big question we're going to explore is, why? Why is the universe expanding? It's not like it's a balloon someone is blowing up. So what invisible force is pushing everything apart? This mystery is one of the biggest puzzles in all of science. Answering it takes us on an incredible journey through time, from the very first moments of existence to the far-off future. It's a cosmic detective story, and we're going to follow the clues together. Think about it this way: if you bake a loaf of raisin bread, before we can figure out why the universe is expanding, we should probably agree on what the universe even is. In the simplest terms, the universe is everything, and I mean everything. Every star, every planet, every galaxy, every black hole, every speck of dust, every single atom, all of space, all of time, all the laws of physics. There is nothing outside the universe. It's the definition of all that exists. It's the biggest possible container. There's nothing for it to expand into because it contains space itself. When we look up at the night sky, we're seeing just a tiny fraction of our local cosmic neighborhood. All the stars you can see with your eyes are in our home galaxy, the Milky Way. But our galaxy is one among an estimated 2 trillion galaxies in the observable universe. 2 trillion. Each galaxy is a massive island of stars, gas, dust, often containing hundreds of billions of stars, many of which likely have their own planets. The sheer scale is almost impossible to imagine. That's how everything can move away from everything else without a central explosion point. For a very long time, scientists, including the brilliant Albert Einstein, believed in a static universe. They thought the cosmos was perfectly balanced, neither growing nor shrinking. It seemed logical. Gravity, after all, is a powerful force that pulls everything together. So, shouldn't the universe be collapsing under its own weight? Or at the very least, shouldn't gravity be holding it in a delicate equilibrium? This idea was so strong that when Einstein's own equations of general relativity suggested the universe should be dynamic, he added a special term, the cosmological constant, to force his math to produce a static universe. He later called this his biggest blunder. The first big clue that the universe was not static came from an astronomer named Vesto Slipher in the 1910s. He was studying what were then called spiral nebulae, which we now know are other galaxies, using a technique called spectroscopy, which splits light into its different colors. He made a startling discovery. The light from most of these nebulae was shifted towards the red end of the spectrum. As we'll learn more about later, this red shift is a telltale sign that an object is moving away from you. Slipher found that nearly all the galaxies he observed were racing away from us at incredible speeds. This discovery set the stage for one of the biggest revolutions in scientific history. If the universe is expanding, then it logically follows that if we were to rewind time, the universe would be shrinking. If you keep rewinding, farther and farther back, all the galaxies would get closer and closer together. Keep going, and all the matter and energy in the entire cosmos would eventually be squeezed into an incredibly small, hot, and dense point. This idea is the foundation of the Big Bang theory. It isn't an explosion in the traditional sense, like a bomb going off in the middle of empty space. Instead, it was the beginning of space and time itself, an expansion of the universe from an initial high-density state. About 13.8 billion years ago, everything that is now our universe was concentrated in a singularity, a point of almost infinite temperature and density. Then it began to expand and cool. In the first fractions of a second, the universe underwent a period of incredible rapid inflation, growing from the size of an atom to larger than a grapefruit almost instantly. As it continued to expand and cool down, fundamental particles like protons and neutrons began to form. For about 380,000 years, the universe was a hot, foggy soup of particles and energy, so dense that light couldn't travel freely. Then, a crucial moment happened. The universe cooled enough for protons and electrons to combine and form the first neutral atoms, mostly hydrogen and helium. Suddenly, the fog cleared. For the first time, light could travel unimpeded across the cosmos. This first light is something we can still detect today. The person who truly cemented the idea of an expanding universe was an American astronomer named Edwin Hubble. In the 1920s, working at the Mount Wilson Observatory in California, Hubble made two monumental discoveries that changed our understanding of the cosmos forever. At the time, many astronomers still believed the Milky Way was the entire universe. Those spiral nebulae Vesto Slipher had studied were thought to be gas clouds inside our galaxy. Hubble decided to settle the debate by measuring their distances. Using the powerful new 100-inch Hooker telescope, Hubble spotted Cepheid variable stars in the Andromeda Nebula. Cepheids flicker at a rate directly tied to their true luminosity. They're like cosmic light bulbs of known wattage. By comparing apparent brightness to true brightness, Hubble calculated distance. He found Andromeda was nearly 1 million light-years away, far beyond the Milky Way. He'd proven it was a separate galaxy. This first discovery blew the doors open. The universe was much, much bigger. But Hubble didn't stop there. He combined his distances with Vesto Slipher's galaxy speed data. When he plotted the points, a simple relationship emerged. The farther away a galaxy, the faster it was receding. That relationship became Hubble's law, Hubble-Lemaitre law. This was the smoking gun. Galaxy speed was proportional to distance, not random. Exactly what a uniformly expanding universe predicts. Think of raisin bread rising. A raisin 1 inch away might move 1 more inch as the dough rises, while a raisin 4 inches away moves 4 inches in the same time. So, how exactly did astronomers like Vesto Slipher and Edwin Hubble measure the speed of galaxies millions of light-years away? Well, they used a fascinating phenomenon called redshift. To really understand redshift, let's first think about sound for a moment. You've probably noticed how the siren of an ambulance sounds higher-pitched as it comes towards you, and lower-pitched as it moves away. This is called the Doppler effect. The sound waves get compressed as the ambulance approaches, leading to a higher frequency and higher pitch. And they get stretched out as it moves away, resulting in a lower frequency and lower pitch. Amazingly, light behaves in a very similar way. Light travels in waves just like sound. If a light-emitting object, such as a star or a galaxy, is moving towards us, the light waves it sends out get compressed. This compression shifts the light towards the blue end of the visible spectrum, which has shorter wavelengths. We call this blue shift. Conversely, if a galaxy is moving away from us, the light waves get stretched out. This stretching shifts the light towards the red end of the spectrum, which has longer wavelengths. This is what we call redshift. Every element, hydrogen, helium, absorbs and emits light at specific known wavelengths, creating a unique barcode of spectral lines. When astronomers look at the light from a distant galaxy, they can see this barcode. However, for almost all galaxies, they find that the entire barcode pattern is shifted towards the red end of the spectrum. By measuring exactly how much the pattern is shifted, they can calculate the precise speed at which that galaxy is receding from us. So, redshift is a direct measurement of how much the universe has expanded since that light began its journey. For decades after Hubble's discovery, astronomers assumed the expansion of the universe must be slowing down. It made perfect sense, right? The universe is full of matter, and matter has gravity. Gravity is the ultimate cosmic brake, constantly pulling everything together. So, while the Big Bang provided the initial outward push, the mutual gravitational attraction of all the galaxies should be acting like a leash, gradually slowing the expansion over billions of years. To measure this slowdown, two independent teams of astronomers in the late 1990s set out to do something incredibly ambitious. They decided to look for very distant supernovae, which are powerful and incredibly bright stellar explosions. A specific type of supernova, called a Type Ia supernova, is what's known as a standard candle. This means they always explode with roughly the same intrinsic brightness. Like Hubble's Cepheid variables, this allows astronomers to calculate their distance with great precision by measuring how dim they appear. The plan was to compare the distances and speeds of very distant supernovae, which show us the universe as it was billions of years ago, with those of closer ones. Everyone expected to find that the expansion was faster in the past and slower today, confirming the slowdown caused by gravity. But when they analyzed the data, they found something completely shocking, something that no one was prepared for. The distant supernovae were dimmer than they were supposed to be. This meant they were farther away than predicted. The only way they could be farther away is if the expansion of the universe hadn't been slowing down at all. In fact, the data showed the exact opposite. For the last 5 or 6 billion years, the expansion of the universe has been speeding up. This discovery was so profound and unexpected that it won the team leaders the Nobel Prize in Physics in 2011. The universe wasn't just expanding, it was accelerating. Something was pushing on the gas pedal, overpowering gravity on a cosmic scale. This unknown something was given a name: dark energy. The discovery of the accelerating expansion of the universe led to a staggering conclusion. About 68% of the universe is dark energy. 27% is dark matter. Normal matter is only 5%. That means 95% is stuff we can't see or understand. Dark energy seems to be a property of space itself. It's like an anti-gravity force woven into the cosmos. So what is dark energy? We don't know. It's one of science's biggest mysteries. Leading idea: Einstein's cosmological constant. Dark energy could be the intrinsic energy of the vacuum. As space expands, more vacuum energy appears. That extra energy makes space expand even faster. The result is a runaway feedback loop: accelerated expansion. This makes dark energy very different from normal matter. Matter and radiation get diluted as the universe expands, but dark energy density stays roughly constant. Matter thins, gravity weakens, dark energy stays strong and becomes dominant. That's why acceleration began about 5 billion years ago. The discovery of dark energy and the accelerating expansion has completely reshaped our ideas about the ultimate fate of the cosmos. The most widely accepted scenario, based on what we know today, is often called the Big Freeze or the heat death of the universe. As the expansion accelerates, galaxies that are not gravitationally bound to our own local group will be pushed away from us faster and faster. Eventually, they will recede from us at speeds greater than the speed of light. This doesn't violate Einstein's theory because it's the space between us that is expanding. When this happens, their light will never be able to reach us again. One by one, the galaxies will disappear from our view, leaving our local group of galaxies as a lonely island in an empty, dark void. Within our remaining island of galaxies, stars will continue to burn for trillions of years. But eventually, the fuel for new star formation will run out. The existing stars will one by one burn out, becoming cold, dead remnants like white dwarfs, neutron stars, and black holes. Even these remnants will eventually decay or be swallowed by supermassive black holes, which themselves will evaporate over googles of years through a process called Hawking radiation. In the end, there will be nothing left but a faint soup of particles and radiation, getting ever colder and more dilute as space continues to expand. The true fate of our universe remains one of the final chapters in this grand cosmic story, a chapter that is still being written.